Now, it is easier to understand the effect of upsampling, in fact, by a general factor of m in the z domain. So, let us begin with that. Let us consider a general factor of m, upsampling by m most generally. What do we do when we upsample by m? That is easy. You see, the original sequence is x of n. So, this is the input. After upsampling by m, let the sequence become x u of n. Now, we can write down x u of n explicitly in terms of x of n. In fact, instead of doing that, let us straight away go into the z domain. So, let us consider the z transform of x u n. That is easy. Summation n going from minus infinity to plus infinity, x u n z raised to the power minus n. And the only catch is, among all these n's, only those n's have a non-zero sample which are multiples of capital M. And therefore, we can rewrite this summation here as summation again. Let us say k going from minus to plus infinity, x of k. Now, remember, x of k occurs at the point m times k in x u m, and therefore, here we have z raised to the power minus capital M times k coming up. Now, this is a familiar expression. This is very like the z transform of x, except that you have replaced z by z raised to the power capital M. So, in fact, there we have a very simple relationship for x u z to x z. Indeed, the z transform of the sequence x u n, namely x u z, capital X u z, is the z transform of the sequence x with z replaced by z raised to the power m. Simple. Now, in fact, this also brings before us very clearly the invertibility. So, just as you can say x u of z is x of z raised to the power capital M, you can also say capital X of z is x u z raised to the power 1 by m. So, what we are saying in effect is that this operation of upsampling by m, this operation is invertible. Clearly shown here, clearly evident. Whether we look at it in the time domain or whether we look at it in the z domain, this property is evident, the invertibility. Very soon, we shall look at the downsampling operation, and there we shall also see the non-invertibility evident in the z domain. Perhaps not as evident, but evident all the same. So, let us now go to downsampling. Now, as I said, downsampling is a concatenation of two processes. In one process, we kill some samples. In the second process, we compress the so called partially killed sequence. This process of killing some samples is what requires a little bit of effort to express in the z domain. And here we shall not attempt straight away to jump to generalization to any capital M. We shall instead take capital M equal to 2, illustrate the idea and then allow for a generalization to any other capital M. So, let us proceed then with downsampling by a factor of 2 now first. So, here we are. When we wish to downsample by a factor of 2, what we are saying in effect is we are killing every other sample. And how do we kill? One way to kill is to multiply by a killing sequence, so to speak. So, when we consider downsampling by a factor of 2, the first killing step can be viewed as a modulation step. Or multiplication by another sequence, by killing sequence, let us call it. Instead of giving such a violent name, maybe we should call this a window sequence, that is a milder name. You know, what does a window do? A window allows you to see a certain part of the scene outside. In a certain sense, when we retain some samples and destroy all others, that is exactly what we are doing. We are allowing those samples that are retained to be passed through the window and those that are destroyed to be stopped. So, if you wish, we can call this sequence that keeps some and removes the others as a window, but a window periodic sequence. You know, I use the word window periodic sequence because the window sequence name has also been used in the design of finite impulse response filters. And the window periodic sequence has the following pattern. At the point 0, it takes the value 1. At the point 1, it has the value 0. And then periodically thus. And the same on the negative side. Periodically continued on both sides. So, you know, you can think of it as a periodic window where wherever there is a 1, you are allowing the scene to pass, and wherever there is a 0, you are stopping the scene. Let us call this periodic window sequence PWN, where the P is to denote periodic and the W subscript is to denote the window behavior. So, this is a window periodic sequence for downsampling by 2.